Okay, should we start? So let's start. As I said in my message, like giving a complete account of this DC calculus with all the proofs looks quite an enterprise. And there are actually some parts I'm not even sure that I can really make, but at least I can give you an idea of what is going on. Okay, so first of all, let me remind you some of the things about Alexandrov spaces that we learned in the last seminar. So I'm going to take the definition that X with a metric P, okay, is an Alexandrov space and for simplicity, let me just focus on the curvature being positive, just because I can simply make comparison with usual triangles. Okay, with sectional curvature bigger or equal than 0, if, okay, so X, how do we call it? It's a length space, geodesically complete. I'm not going to like, let me just say X is a geodesically complete. Let me even say X is geodesically complete metric space.
Mean that between every 2 points.
Between every 2 points, I have a between every 2 points, I have a minimizing geodesic. Okay. And I have a comparison with triangles. So, and there is a comparison with Euclidean triangles. Okay, and that is in the following sense. So if I take 3 points A, B, and C, okay, and I look at the corresponding triangle in the Euclidean space, which is the comparison triangle. So it's a triangle with the same length. So these sides have the same length. Okay, so what I want is that for every point that I pick over here, for every point P, the length of the geodesic connecting A and B is being strictly bigger than the length of the geodesic, which is connecting A and say, let me call it A bar, B bar, C bar, and here I have P bar. Okay, and okay, the stipulation is that this length is the same. So the triangles are thicker, as the picture, one of the few pictures that I can actually make, right? Okay, and let me say that what we learned from the seminars of the last semester is that there's lots of nice things that you can do. So first of all, we learned that there's plenty of equivalent definitions which have to do with comparison with the angles rather than like this comparison over here. But this one is the one which is most convenient for me, as you will see somehow in a few minutes. So there are several equivalence definitions. You can attach a concept of dimension, class of dimension, and we are just going to assume that the Alexandrov space is n-dimensional. Okay, so, and here, one of the theorems was that there was a definition of being n-dimensional by looking at the maximal number of, say, points that we can find in a position, in a certain position, but then finally this was proved to be the same as saying that the intrinsic metric Hausdorff dimension is an integer n, so that is true for every Alexandrov space. It's either an integer n or it's plus infinity, and it has even finite hn dimensional volume. So Let me just assume that Hn, say, under this assumption, I could say is sigma finite. Okay, and from now on, let us just restrict our attention to actually compact points.
Sorry, I didn't, I don't know what that means.
Sigma finite,
I thought I knew what sigma finite was, but I don't know how to.
Hn,
Yeah.
a Hausdorff n-dimensional measure.
Oh.
That's just a Hausdorff measure.
Okay.
Define it by
Okay,
using,
okay.
define it really by using the metric. Okay, so from now on, assume X compact. Okay, so in the theory that was developed in the first semester, we saw that we can always attach to each point a set of directions. So, which is usually called something like sigma x. So the set of directions, you can think about it as by like looking essentially at, I mean, like ideally would be the tangent to the point, and it's the set of points. I mean, like you define it as, say, if you had a good exponential map, you would define it as the tangent vector of the geodesics which are exiting from the point, tangent vector, of course, of length equal to 1, but then one way to define the set of directions is to make a quotient by, say, the geodesics, which are like getting out by saying the two geodesics are equivalent if they have, say, the same tangent at the point. Okay. Okay, and what was important is that, okay, so the set of direction is itself an Alexandrov space. Of curvature k bigger or equal than 1. If the curvature over here is bigger or equal. Is it good? That's actually independent of that. That's always the case. Okay, and somehow you can.
Sorry, the Alexander space. That's. Are you taking the union over all the X, or are you just?
No.
At one
Just
point,
that one.
just
At one point.
Just the tangent. So
At
this
one
is the
point.
replacement for the tangent.
Exactly. This is the replacement for the tangent, or better said, the cone over it is actually the replacement for the tangent. Okay, so the cone over sigma x is the replacement for the tangent. As Karen's saying, so it's what we call the tangent cone. And somehow, one of the things which were proved, or at least were mentioned in the last semester, is that one effect of the theory is to tell you that actually the sigma x is going to be the unit Euclidean sphere, and this tangent cone is really going to be the Euclidean space on a lot of points. And these are, in some sense, the regular points. So a point is regular if sigma x is actually say the n-1 dimensional sphere with the standard metric.
I mean, some intuition here, though, is if you're just in a regular space, right? The tangent cone always has curvature one. I mean, and
Yeah, the sphere, the unit sphere of the tangent cone. Yes.
yeah, no, so in this case, however, we need the curvature.
In this case, we
of
have
the-
an inequality.
in this case, we need the curvature of the base Alexander space to be greater than or equal to 1 in order to know the curvature.
Okay, so greater or equal than 1 is not really important.
Oh, it's not important.
So just
Okay,
bigger or
that's
equal
good.
than 0 or bigger or equal than any. I mean, bigger or equal than 0 is what I guess we used in the proof.
Yeah,
But if you use, I mean, because these spaces, you can actually look at them as limits of the scaling in the Gromov-Hausdorff
right,
sense.
yeah.
I mean, if you just have here a negative number, when you be scaling, that negative number gets closer and closer to 0.
Yeah.
So at all effects, that operation is the same as soon as you have a lower bound.
Yeah, okay.
But we are leveraging the lower bound to understand that this tangent has curvature in the Alexandrov sense, which is bigger or equal than 1. Yeah. I mean, this one is really the set of direction. It's maybe inappropriate to call it. It's the set of unit tangent vectors, if you want, right? That's the idea. Okay, and so what did we prove? Well, if I remember correctly, the space of singular points has 4 dimension 2 even, right? Let me just say, so the dimension of x minus the set of regular points is, I think, at most n minus 2, if I remember correctly.
Did we prove it?
Sorry?
Did we prove it?
Maybe we didn't prove it.
We discussed that
We discussed
that they are regular points never dense, for example,
yes.
and that there are these Lipschitz Lipschitz correspondences with.
Yeah, I remember we also talked about the stratification and we talked about the set. I don't remember if we just said that this one is less or equal. If we proved that it is less or equal than n minus 1 or n minus 2.
Hi, Camilo. I think
in the talk you gave to announce what would be.
It's going to be a subset of the rest. That's what you mean.
That was my perception.
Okay,
But they
okay,
announced
okay.
that.
Well, I'm
First
pretty
distance.
sure we at least proved that it has measured 0. Right? Or that it is dense at least.
Dense, yes.
Okay, so let me take it back then. Oops.
G delta dense.
The regular.
G delta dense.
Yes.
Right. Yes. Okay, so we proved the regular set is G delta dense. Yeah, you're probably correct. It's actually over here. Yes, okay. So it's actually one of the theorems possibly which is covered by one of the several places here in the literature. So okay, so in fact, this is one of the theorems. Correct. That's actually Otsu and Shioya in JDG. It's 1984. Okay, that the dimension of the complex of the complement of the regular set is actually equal to n minus 1. And in fact, yeah, I should have been more careful. So when you actually stratify, since actually the Alexandrov space might have a boundary, I think that kind of the stratum, I mean, like what you could find the set of possible tangent directions, which is like a half space, and that is going to be the boundary. And so if you call that boundary, the real singular set is going to have dimension n minus 2, I think. That would be an effect of the stratification. So maybe here I should make a remark. So note that by our definition, x minus regular of x would contain the boundary of x if just x were of x if x were an honest Riemannian manifold with boundary. Okay. So the other thing that we proved is that there's a kind of slightly better set, right? So the set which is strained.
Sorry, can you repeat the remark? The point of the remark.
This remark over here?
Yeah.
So by the way we have defined our set of regular points, if you were to apply our definition to an honest manifold with boundary, the boundary points wouldn't be regular points according to our definition.
Right.
Because we make the tangent cone, and the tangent cone is going to look like half space.
Yeah.
So the complement would actually contain the boundary of x.
Oh, minus regular. Right.
Minus regular, which means that, okay, calling the complement of the regular set singular set is a stretch if you have this boundary, because I mean, like, okay, with the boundary, that would be actually a nice point. I didn't. So there is this is said by Petrunin in one of the things which I have over here. There is a way to get rid of the boundary, because if you glue the Alexandrov space, another copy of the Alexandrov space over the boundary points, you actually get again an Alexandrov space, and you can eliminate all the boundary points. At that point, what would be left of the x minus the regular points of x are really kind of things where you, when you make this rescaling, you should see an object which has at most n minus 2 symmetries, which means that then that set actually should have dimension n minus 2 really. Okay, so that's what I just wanted to say.
But you have to define the boundary. I mean, I guess.
Yeah, you have to define the boundary.
But I mean, even if it were a manifold, presumably the boundary might not be smooth. And so when you actually.
The condition that it is like geodesically complete.
I agree with that.
Kind of too complicated.
Yeah.
Yeah.
Yes.
Yeah.
So
Oh,
the condition that you're geodesically complete makes the boundary concave,
Okay, right.
convex, depending on
Yeah.
the direction you're looking at, which actually makes it automatically not that bad.
Okay.
Okay, and then, but, okay. Anyway, so now that was another thing that we said, and that's going to be our starting point. We cancel this. That is going to be the starting point. So that there is an even larger set. Okay, so okay, so first of all, let me define what are the n delta prime strained or n delta strain points. Right, so these are the points. So this is the set of points P. So P is an n delta strain point if there exists two n other points. So these are like, let me call them P1, P2n with the following properties. Okay, so when I look at the angle, here I have to be careful. So when I look at the angle, so this is really the angle. So this is the angle with the tilde. So it's really the angle in the it's really the angle in the space. Okay, so when so for each, so there are two n, and essentially for each of them there is a corresponding guy which is almost like on the opposite line. Okay, and in general, if we take now I and j with j not being equal to I, the angle which is formed between the two of them is at least pi alpha minus delta. Okay, so essentially you have, for instance, in 2D a picture like this, right? I mean, this forces all of these angles to be roughly pi half, right? With,
If we are n dimension.
sorry, in dimension. Sorry.
If we are n dimensional.
If we are n dimensional,
Yeah.
right? Exactly. And this n is the dimension of the guy. And actually, what we proved in our first series of seminars is that if you take the n, which is maximal, that is the dimension of the Alexandrov space, and for that dimension, it is hn sigma finite and all of the sort of consequences. So the actual dimension of the Alexandrov space was just defined by looking for each point, what is the maximal number of strain points that you have, and then by taking the maximum among all possible points. Okay. And then, of course, what you get as a corollary is that on this G delta set, essentially the thing is homogeneous, it's all the same dimension. Okay, and what is the nice thing is that this xn delta, okay, which contains the set of regular points, right? Because I mean, in the set of regular points, if you go closer and closer, you find something which is closer and closer to the Euclidean space. So you're actually finding closer and closer lines to like, you know, be really like not broken and sort of orthogonal. So if you take delta sufficiently small, this guy is a topological manifold. And I think we proved certainly that the charts are ordered, but in fact, the charts are even by Lipschitz, right? Okay.
This is just for delta sufficiently small, or
For delta sufficiently small. Yes, 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 yes.
So we're looking at a topological manifold, but it has some other points,
Yeah, there are
The
some
ones that
points which
not
are left
in
over.
XN,
Yes,
They're not in XN. though.
yes. And there's really no way you can, like, you know, get over that, because you can take, for instance, say, a bad manifold with positive sectional curvature, make a cone over it, and at the tip of the cone, that bad manifold will not be homeomorphic to any copy of the Euclidean space.
Oh, I see.
So it's really, I mean, you can't push it further.
So it's an open set.
It's an open set.
Okay, it's an open subset of.
It's an open subset of that. Yes, yes, yes.
So the delta depends on x as well, right? Of course.
Sorry?
The delta depends on x as well. I mean, the delta such that delta is sufficiently small.
Okay, so maybe x and delta I haven't defined. So let me just tell you, x and delta is the set of points x and delta strain. So that is a definition.
Right.
If you go at a very singular point, there might not be any n delta strain guy. Okay.
No.
So now x and delta is the set of points which are n delta strained. But for a fixed delta, I'm not talking about points. And then the theorem is telling you that there's a fixed delta such that
Depending on x.
depending on n,
Just
only on the
n.
dimension.
Yes.
Yes.
Okay.
Just n. Okay, so it's not depending on x.
So the delta doesn't.
No, no,
Okay.
it's a universal constant.
Okay, okay.
If I am,
So we.
if I am, I think the
So
theorem correctly.
intuitively, we might think that these is cone points.
Yeah, okay, so these are the cone points with the cone which is kind of sufficiently flat, right? Sufficiently close to the Euclidean
I mean,
space.
the x minus xn delta.
These are cone points where, yes,
And intuitively, they are codimension two.
yes, intuitively they are codimension two.
We proved it, I meant.
Yeah, okay, intuitively they are codimension two once you take away the boundary though,
Yeah.
because the boundary is also there, okay? It's kind of fake
Much
cone
clearer
points.
what these spaces are gonna look like. Okay.
Yes. Yes, yes. And somehow this theorem is essentially telling you, well, like, you know, which is intuitively kind of clear, when you get sufficiently close, I mean, when you get sufficiently close to the Euclidean space, you would actually be homeomorphic to it. That's what it's saying. Okay, so now what is the DC? So now what is the DC calculus, which should be the so this idea of Perelman. So actually, you can put charts, so you can make this topological manifold much better. I mean, it's already by Lipschitz, so it's not that bad, but you can make it almost having a second order structure, because you can actually make the charts So DC manifolds. This is formally defined as a topological manifold X with an atlas A with the property that the coordinate changes, okay, which is called this way, right? So A is the atlas, which is going to be like U by U. Okay, so right, so if it is correctly, no, it's the other way around, right? The minus is over here because this is the trap, so it's going on to the Euclidean space, and now the change of coordinates is going from the Euclidean space into, I mean, from an open set of the Euclidean space into another open set of the Euclidean space. No, so it was correct before. Okay, so this one, which goes from, say, I U of U intersected phi. Yeah. It goes from IV of U intersect V into U intersect V. Okay, so this function, which is our change of coordinates, is the difference of convex functions. Okay, so in fact, it's even slightly better. And let me just put this DC 0 over here. And let me make just a little digression into convex functions. I mean, if I'm saying something that you guys all know, you just stop me and I will not go further with the digression. So convex functions are continuous outside a set of codimension n-1. So that's a fact about convex function. And it's actually maybe I should say effects of convex functions. So these guys actually like it to call it difference of concave functions. I have a psychological problem in doing that. It's completely equivalent, of course. So facts about convex functions. Well, when you have a convex functions for every x, you can define the subdifferential of f at the point x. Okay, so this is the, I mean, if you think about it in terms of hyperplanes, this is just the set of supporting hyperplanes. So it's the set of hyperplanes which are touching the graph of the function from below. And I'm looking, of course, at the kind of at the psi, which is defining the hyperplane. So this is going to be the psi such that your function f at any point y is going to be bigger or equal than the value of the function f at the point x plus psi times y minus x. Okay, and one basic fact, of course, about convex functions is that if you have a convex function, say on an open set, when you go actually on a compactly contained set inside, you're just Lipschitz. So there's always going to be something in this. And this something is also bounded. And now this one, I mean, this sub-differential is immediately, I mean, you see it immediately from the definition. It's a closed set. It's also a convex set. And now you can look at the points and stratify them according to the dimension of the subdifferential. Because it's a convex set, it's going to have an intrinsic dimension, which is easy to pick. And then you can prove that the set of points where the subdifferential has dimension, say, k, that set has actually dimension n minus 10. And the subdifferential is upper semi-continuous, even that you see immediately, right? So because if you have a set of points which is converging to another point and the set of points in the subdifferential is converging, it's an inequality stable. So if you're lucky and your subdifferential is a point, well, for approximating points to this particular point P, the subdifferentials have to shrink and they all have to converge to this particular point. And what does that mean? It means that, well, the points where you have a single subdifferential, those are the points where you're going to be actually differentiable. And at those points, so this is what I wanted to say, not that the function f is continuous if the function f is convex. That's kind of silly because it's Lipschitz, is that the gradient of the function is actually continuous, except for the points where this one has dimension n minus 1. Okay? And less or equal than n minus 1. So what is dc0? Okay, dc0 is, I'm assuming that the charts, that those functions over here, they're not going to have the top n minus 1 dimensional guy inside. So that they are continuous, I mean, the gradient is continuous if you take away a set of dimension n minus 2, actually. Okay. Okay, so these are the dc0. Okay, why do we like the dc0?
Can you repeat like?
Sorry?
Can you repeat again, just what is dc0 and just?
So dc0, okay, I'm just going to say it's a difference of convex functions which are continuous except for a set of dimension n minus 2.
Gradient is continuous.
The gradient is continuous except for a set of dimension n minus 2, which amounts to assume that the set of points where the subdifferential has dimension n minus 1 is absent.
Is what?
Absent. It doesn't exist.
Does
Yes. So, yeah.
And when you say that the function from Rn to Rn is a difference in convex,
Sorry, it's a set of points. Sorry, I said it wrong. It's the set of points where the subdifferential has dimension 1, not n minus 1, because they are the fattest ones. Okay?
P sub u composition P sub b inverse the difference of convex in the sense that every coordinate of it is a convex.
Yes. Sorry. Exactly, because this is a vector function. Very well. Thank you very much for. In fact, this is the whole thing, which is kind of really problematic. Is that it's kind of okay? Is each component is a difference of complex functions, and that's kind of creating lots of problems. Okay. Yes.
You know, there is a characterization of this function. Well, I guess because of the name, there isn't, but just if there is a characterization of them that is like a test rather than there exist certain functions so that it is a difference than other.
It's a good question. So since we will actually suffer a lot to just show that something is bloody a difference of some complex function, would be nice, but I don't see a nice way of doing that. Okay, so one thing that you immediately see is the following. So since the function f is convex, the second differential of the function is going to be a Radon measure. Okay, which is going to be part of the, why you can have some sort of second order calculus over there. It's a Radon measure. So now certainly if I give you, say, a function f with an Hessian, which is a Radon measure, and I try to write it as a difference of convex function, that only works in one dimension. Because this property that for instance, of the continuity and so on, I think it's false if you're just going to look at a general function f whose second differential is a Radon measure. I mean, like, of course, what you can't do, if you are in one dimension, you can just take the positive part of the measure, the negative part of the measure, and you integrate it twice. But if you're in higher dimension, when you actually try to truncate things meaningfully, you're going to run into problems because you don't know that the truncation is something which is integrable, right? I mean, because being the Hessian of something is very restrictive for a matrix.
Do we even know that like each individual part is integrable? Like, can it be the case that?
Yeah, it's very, very problematic, right? I mean, even if I give you somehow, say, a W22 function for you, I mean, W21 function somehow. So that the Hessian is kind of in L1, like, even if it is a very nice measure, when I try to kind of decompose it into like, you know, positive and negative definite parts, I'm going to run into a hell of a lot of troubles. Okay, so here it is. Why are these DC manifolds, why they are actually so, okay, so why is it natural to do this stuff? So first of all, I have to say something. So there is this little lemma, which tells you the following, that these DC and DC0 functions, they are in algebra, and they're even well behaved under composition. So let me make this the following lemma. So the C functions are closed under composition. So this means that if G, say from U to R, is a difference of convex function, and F1, Fn are difference of convex functions, then G of F1, Fn are difference of convex functions.
Oh, DC is difference in convex function.
Yes.
Okay.
It's not Washington. Okay, so this is something which nobody proves actually in any of these references. So either you do it as an exercise, which is far from obvious. Either you do it as an exercise, which is far from obvious, or you find somebody that does some textbook that does it. Anyway, so here's the proof. It's easy, but it's not obvious, though. I don't think so. Okay, so of course, one thing which is nice is that the composition is linear on this part, right? So I just can restrict to prove it if G is a convex function, right? Oh, okay, so one stupid way of trying to do it would be to go and make a lot of brutal computations. It doesn't bloody work somehow. And it's again this problem that is difficult to integrate stuff. I mean, like in 1D, you can come up with this sort of silly proof by just trying to, like, you know, differentiate and so on. But in 1D, it's obvious. I mean, in 1D is obvious because as soon as I know that the second derivative is a Radon measure, I decompose it into positive, negative part, and I integrate. So I just need to show that. If G composed, the G composed F has a derivative which is a Radon measure, and that's relatively easy, because when you're actually differentiating, you find G prime composed F prime times F prime, and then you find G second composed F prime times F prime squared, or G prime composed F times F second. But because you're a difference of convex functions, the derivatives are Lipschitz. So you multiply a measure by something bounded, you measure and you're happy, and you can decompose it into like, positive and negative part, and you integrate. If you're trying to do it in higher dimension, it's a very bad thing. Okay, so proof without loss of generality. G is convex. Okay, so now you write G. So you write G of Y as the supremum over X in omega of, well, I'm not even telling you, like, over some family, some index. After all, we are on the Euclidean space, so we can even just think that the index is countable of AI plus BI times Y, right? So it's a soup of linear functions. But now, since I can go a little bit on the interior where G is actually going to be Lipschitz, I can assume that all of these constants and all of these BIs are actually bounded, okay? A priori. That's because without loss of generality, I can assume that G is convex and Lipschitz. Because I can go a little bit in the inside. Okay, and so now let me write each of these Fi's as Fi plus minus Fi minus. So one is the convex and the other one is the concave part, okay? Because I have as an assumption that they are the difference of convex functions. And okay, so now G composed F is the soup of AI plus BI. And then here I have the scalar product with Fi. Okay, this one is a bad notation because you're Fj, and now I'm in F plus, you might imagine what it is. Okay, now you would be so happy if these coefficients were positive, right? Which is completely unrealistic because these are vectors with arbitrary component, and here there's even a minus sign. So some of them is going to be negative for sure. Okay, but now you can replace, replace all of them. Okay, so replace the, make the following. So define b tilde I to be m plus bi, and let me actually do it this way. So b plus I to be m plus bi, and bi minus to be minus m plus bi. Okay. Or m minus bi. So, the components. So okay, so these are vectors, even though I have this index I over here. Okay, now these are vectors of positive numbers, which make me extremely happy. And I need to see what is the difference. right? I mean, now here I'm extremely happy because this is a positive linear combination of convex functions. So it's convex, and I take the soup. But then, of course, there's something which is not okay, which is that I have minus m times the sum of fj plus, right? Because I have added m over here. And I have minus m times the sum over j of fj minus. Okay, but now I'm extremely happy, right? So this one is convex. And of course, now I can put these two guys together, take the m outside, and this is convex too. Okay, so then it's the difference of two convex functions. Okay, so now here should be a theorem, and that's a theorem that I've been trying to understand, at least at an intuitive level. And the theorem is that, so this is the theorem of Perelman, that so these charts, the charts over here can be made difference of convex functions. I mean, can be made so that the change of coordinates is a difference of convex functions. So. A delta. So I'm not so sure if he can keep the whole x and delta. Let's promise it in this way. So he's a DC manifold. And in fact, it's even a DC zero manifold, but I already have problems understanding his argument for the DC manifold. Okay, so let me give you the intuition at least. So I think I've got a good intuition of why it is true. I mean, his proof saying sketchy is generous. It's a sketchy, and he refers to a lot of other literature which have been trying to chase it out. I mean, his own papers, some Russian for which I found the translation anyway. So, but at least I think I got the intuition of it. Okay, so first of all, and here is kind of the fundamental remark. Well, there are a couple of fundamental remarks. This one is kind of the easy one. So, if you remember the proof of this statement, the proof of this statement was that locally the charts in the point P were constructed by picking the strainer and picking the distance of the point P to the points Pi's in the strainers as coordinate functions. Okay, so in the proof of the By-Lipschitz structure, the chart, so let's say phi, so this is comprised by n functions, so they were the distance from some point Pi's. Okay, let me use the notation which is used in Alexander spaces. I mean, if I were me, I would put distance between Pi and P, but that is pretty cumbersome. So the notation which is typically used is just to write this one here. So this one would be the length of any geodesic segment, which is length minimizing and which is connecting P and P1. Okay. if you're me, you're used to think that this guy is a convex function, right? The distance function is convex. But not these guys, actually. So you have to think that the distance function is semi-concave. Okay, so first of all, let me give you a definition. So, definition. Okay, so a function. Well, first of all, let me give you the definition in the Euclidean space, right? So a function is semi-concave in the Euclidean space if there exists a constant such that f of x minus, let me take this constant positive, minus lambda modulus of x squared is concave. Okay. So which amounts just to say that the second derivative of f is bounded above by lambda times the identity. Okay, so I cannot reach infinity from the right side, right? Okay. Now, in Alexandrov space, you can give the same definition by resorting to geodesics. Okay, so now you're just going to say, so in an Alexandrov space, say f is lambda semi-concave if, okay, for every gamma geodesic parameterized by arc length, when I look at f of gamma of t and I subtract lambda t squared, this guy is a concave function of t. Oh, and now the distance function, as long as you stay away from the point P, I, P1. But I mean, in a sense, somehow this was serving as a chart. I mean, remember that we had somehow this strainer. This was serving as a chart in a very small neighborhood of the point P. It's very far away from the endpoints of the, I mean, from the PIs. Okay. So now the idea is that in an Alexandrov space, it's obvious that the distance function is geodesically concave, and the reason is the following. So in the Euclidean space, the distance function is geodesically concave. Just a simple computation because it's a smooth function. In the Alexandrov space, the distance function can only go up, which is exactly the place where the inequality is going if you're looking at concavity, right? So formally, we really want to be pedantic. So here's your point P. Here is your geodesic gamma, which has a starting point A and a starting point B. Okay, so the concavity inequality, what is it? Okay, so if I call this function, say, g of t, or let me just do it in this way. So the concavity inequality, if I call g of t to be equal to p gamma of t minus lambda t squared. Okay, what you want to actually prove is that g of alpha t plus 1 minus alpha t is bigger or equal than g of t times alpha plus 1 minus alpha g of t. Okay, and now what I'm going to do is I'm going to like take a comparison function which I call gc of t. In the comparison function, I take the corresponding triangle in the Euclidean space, P, A, and B, bar. And of course, the corresponding triangle is defined in such a way that P bar, A bar, P bar, B bar is the same distance as this one, okay? So for this guy, you have this inequality with some lambda. Sorry, this should be really between 1 and 0, right? Right, so because, okay, so here is like gamma of 0, this one is gamma of 1. Okay, so okay, but exactly because of the comparison, somehow this thing actually happens to be exactly equal because the two segments are equal, whereas this inequality is going larger than that inequality. Okay.
So maybe it's equivalent.
Sorry?
Maybe the two are equivalent. That is the comparison.
Yeah, it's essentially equivalent to the concavity of the distance function. Yes, I mean it tells you the distance function is more concave.
Comparison and the statement of concavity.
Okay, so now you have something very nice, right? Because these functions are semi-concave directly. Now here's a little issue though. So in the Euclidean space, it's absolutely obvious. If you have a semi-concave function, it's the difference of two concave functions, right? It's less obvious in the Alexandrov space. And in fact, you need a lemma, which is in one of Perelman's papers, but not the one on DC calculus. So he says, well, okay, like, you know, just being semi-concave because there's an abundance of very concave functions in small neighborhoods, CP, and P is the element of Morse theory on Alexandrov spaces, for which I first printed the Russian, but I cannot yet read it, and here there's the translation. So there's a lemma over there which is going to tell you that as soon as you are semi-concave, then you're also difference of concave functions. Okay. Now that lemma is not actually what bothers me most. So I've been trying to understand what is actually what seems to be the most difficult part of it. So that one is a chart, right? The change of coordinates is going to be the composition of the inverse of some chart with another chart. Now, the inverse of, okay, so it's true that it is an algebra, and it is true that it's closed under composition, but there's no bloody reason why the inverse of a function which is made, whose components are made by semi-concave functions, or like difference of concave functions, is going to be a difference of concave functions. I mean, that is kind of quite peculiar. Okay? Okay, so let me give you an attempt at explaining this proof.
So it seems like they are like a function. Like if we zoom very much, it seems like just like a linear function with gradient 1 plus something small.
Yeah, at that point I start being more optimistic about it. Yes, at that point I start being more optimistic about it. But that's not what he's using. Okay, so here's what he's doing. So first of all, So first of all, he's using charts which are particular. Okay, so okay, the charts that you really like are done in the following way. So you have points P1, Pn. So these are going to be the points for which you have the charts. I mean, which are going to define the charts with distance functions. And they have the following property. So so at the point P, the angle which is formed by PI, PBJ, okay, it's always more than pi divided by 2. Okay.
Minus delta, right?
Sorry?
Minus delta, no?
No, plus that. He likes to be a little bit obtuse. Okay.
Is it only for like half of the piece?
All I different than J.
Okay, only J is only from 1 to n, not also the other half.
Yeah. So I'm forgetting about the rest of the string.
So you choose the ones for which you are larger.
So you choose the ones for which this one is a little bit more than pi divided by 2. Okay. You've got to prove that these guys are there, huh? Okay. And so what is nice about this? So essentially, so this is a way of understanding it. Okay. Like, let me assume this one is the function f1, this is the function fn. Okay, so what this function fi does over here by this condition is that the scalar product of the gradient of these two functions is always negative. Okay, because the gradient, I mean, if this were the Euclidean space, the gradient is really this direction and this direction with unit length. Okay.
Is it obvious that we, like, I mean, it should be obvious, but is it obvious that we can just shift the point P so that that condition holds?
No, I think so. I mean, like, you will need to construct these guys to have the charts. It's not even talking about that. So if you were in the Euclidean space, this condition would be equivalent to have the gradient fi scalar product with gradient fj is less than 0. Okay. Okay, now let me make the following. Okay, as you're going to see, the proof is actually far from intuitive, but let me call it lemma. And so I can definitely prove this lemma on the Euclidean space. So the lemma is saying if f1, fn are by Lipschitz, and semi-concave, and G is, well, Lipschitz, it's also for 3, but let me just say it. So it's Lipschitz and semi-concave. And moreover, these conditions are true for every I different than J. And the same condition with the scalar product of gradient G with gradient Fi is everywhere negative depth. I mean, it's everywhere like, with this condition. Then the composition of G and with F is semi-concave too. Sorry, the composition of G with F to the -1 is semi-concave as well. Okay, so now, if you were in the Euclidean space, and now instead of having something here which is semi-concave, I mean, like instead of having something here which satisfies this inequality, which you don't know, right? Because I mean, now I'm assuming so G1, Gn are functions which are coming from different charts. I don't know what is the relation of the gradients of these Gi's with the gradient of the Fj's. But if I were in the Euclidean space, I can subtract from each of these Gi's a linear function, which has, a single linear function, which has directed in a way which has a scalar product, which is going to adjust all the other guys, and satisfy this condition. Sort of adjust for the fact that the gradient of G has to be, might have positivity. And then I write G as the difference between G plus this linear function and the linear function, and the linear function is going to have that inequality as well, of course. It's even more direct. Now, so the plan of Perelman is essentially the following. So first of all, prove a lemma like this in Alexandrov spaces, for which I need to give you a definition of what it means to have the scalar product of the gradients between two functions. Okay, and then construct something appropriate to shift, to satisfy this condition. Okay, and so the something appropriate is again a lemma that he credits to okay, let me maybe not go into there, right? So let me just try to convince you that this works in the Euclidean space. So it's far from obvious. And the reason why I came up with this lemma in the Euclidean space is because I can't actually make his proof work literally, but I can at least take pieces of his proof to make the thing work in the Euclidean space.
Sorry, Camilo, in Euclidean space, you really require that condition that the gradients have larger than...
I do.
Okay.
I do. So inverting some casual semi-concave function is going to screw the hell up.
Right, but if you're by Lipschitz...
Even if you're by Lipschitz, you don't know what the hell is going on. I don't think so. I don't think you can hope for inverting a by Lipschitz semi-concave function and hope that in general you compose it with some other semi-concave functions and it's going to be okay. I don't think so.
So F inverse by itself is also not semi-concave.
Okay, so this one is semi-concave, sorry, I should say. Okay, then G composed, oh, it's sad over there, so sorry?
So F inverse by itself is not semi-concave.
No, F inverse by itself is not semi-concave, no.
I mean,
only,
it's not enough to just with some linear function.
Yeah, only if you compose with some linear function.
Okay.
So some linear function composed with these guys will be semi-concave, hence concave, and then you add it to, and so then, I don't know, F1, which would be like the composition of coordinates x1 with, F1 inverse, which would be the composition of, you see what I mean, right? So
No,
the first coordinate of the inverse of F is the composition of a linear function with all the others. but you need to adjust by adding some very large linear function somewhere to actually make it semi-concave.
Wait, but adding a linear function should not change semi-concavity, no? Or because there's a freedom of lambda, or are you saying that for a uniform lambda or something?
I mean, multiplication by the lambda, of course, is going to change semi-convexity or semi-concavity because lambda might be positive or negative, right? So I can't hope.
Right. True, but I mean,
I can't hope. Not every linear function is going to have that property, right? So
yeah, okay, fine.
and I don't know. I mean, I don't know where is the other linear function that I'm adding. I don't know where it is directed. It's maybe directed in another direction to make all of these conditions of negativity.
Okay, sure.
Okay. Okay, so first of all, let me convince about this. So exercise, one dimension. Okay, so one dimension is of course kind of easy. So let me, but it's an instructive computation. So modulo some technicalities, this can be adjusted. So let me assume that I can just take second derivatives. And so all I have to check is that the second derivative is bounded from above. Okay, so this requires some adjustment. It's not for free, but you know, I would need to like use the chain rule in a situation in which I am not that smooth. Okay, but so if you trust me on this, the computation is very easy. So I want to take two derivatives of this guy, right? And so the first derivative gives me g composed f to the -1. And then I have the derivative of f to the -1, which is 1 over f prime composed with f to the -1. Right? And now I have to take the derivative of this guy. Okay, and I'm very happy with the first portion. Because when I differentiate twice, I actually get the square over here. So the sign of my second derivative is not going to change. And now what happens in here is that if you compute this, well, this is what it's going to be. So here you would have f to the -1 prime, which is going to be 1 over f prime composed f to the -1. Okay, so you see what is happening. So if the sign of this guy is minus the sign of that guy, which is exactly this condition in one dimension, so g prime times f prime is less than 0, then this coefficient becomes positive. So g second was semi-concave, so the derivative was less or equal than a constant, and now here I need to use the Lipschitz, the bi-Lipschitz property to say that f prime is bounded below from 0. And here I'm using the Lipschitz property of this guy and the Lipschitz property of that guy, and the fact that the sign is again not changing. Okay. I mean, it's again positive because this one times that one is positive. Okay. Okay, now I know this is going to be ugly, but I didn't find another way of proving this than taking derivatives and make the higher dimensional analog. So now this requires a bit of patience. Yes.
Can the lemma be strengthened to less than equal to 0, or do you need strict less?
No, less or equal would be fine.
Less than equal would be fine.
Yeah, less or equal would be fine. Okay, so okay, so now I would have a f inverse I don't like, so let me call it h. Okay, and h is f inverse. Okay, so now this is going to be bi. right? I'm just applying the chain rule. And now here there's a very nice term, which is going to be the corresponding of that one. So I have, sorry, this is G, and this is H. Okay. Then there's going to be these other things. So, what am I doing? So G composed H. So these are H. These are H, and this is G composed H. This is H. Okay. So when you look at this, this is really the Hessian of G, dH transpose times dH. So when you're going to look at it as a quadratic form, since you have the natural transformation of it, so when I'm applying it on some vector, I'm just going to have that is less or equal than the modulus of this vector of dH of G, which just dH of V, which is magnifies by the fact that this one is a Lipschitz. Okay, so this quadratic form, let me call it Q. When I apply to VV, I'm just going to know that this is less or equal than a constant, and then I have DHV squared. I mean, this is the semi-concavity of G, and this is going to be less or equal than a constant, and now you have the Lipschitz constant of H, and then modulus of V squared. Okay? And now H is F inverse, and I know that I'm by Lipschitz, so I'm very, very happy with that piece. What I'm not so happy with the piece is this guy. And this is becoming more complicated. Okay, so now it's going to be a much more complicated computation. So I have to differentiate this guy, right? Which is the kth coordinate of F inverse. Okay, so first of all, who is this guy? Well, this guy is really the differential of F inverted composed on F inverse. And now I'm looking at the K coordinate and the I derivative, right? So this looks like that. Okay, and now I have to differentiate twice. Okay, so we have first the differential of this, and I am applying the chain rule. Okay, and then I have dj of F inverse and the coordinate F. Okay. Okay, now I need to understand what is this differential. right? So, well, I use the formula that if I differentiate a matrix to the -1, this is equal to the matrix to the -1, the differential of the matrix itself, times A to the -1. Okay, minus.
Just to show.
And that's important, that's important, that's this minus. So no minus, it's not gonna work. Okay, so now let me apply that formula. To this guy, so the F inverse KI. So this is minus the F inverse KS. Now, the F SR the F inverse RI. Okay. So I want to give a name to this F inverse because, and I want to remember one thing. So this one is who. Okay, so this is going to be the F inverse. So L coordinate J derivative. So Lj composed with F to the -1. Okay. Okay, so now let me go back to why did I call this GK? So it's HK, right? So I'm differentiating this guy. So, okay, so Dij HK, now I'm just going to write it in the following way. So there is the composition with F inverse everywhere. So over here, over there, and so on. So this matrix, let me call it, well, let me call it A, ALJ, all of it, composed with that quantity. Okay. So I will have minus, I have to insert this. So AS DLR G DLR F S yes AKS DLR FS. Okay. Then I have this ARI. Okay. And then I have ALJ. So I need to plug it inside this formula. So this is the piece which was problematic. So now B looks like this. So let me just bundle these guys all together and just argue that this one is the second derivative of Fs, so of the S component of F. And then there's going to be A transpose. So this is a piece which I like a lot because it has exactly the same structure as this one over here. So B is going to be dkj, I mean dk of G, oh, and everything is composed with f to the minus 1. But of course, like that one is also composed with f to the minus 1, okay, which is H. So dkg composed with f to the minus 1. Okay, then I have AKS. And then I have A transpose D2FS A. Okay, and there's a minus. Okay, and this one is really the inverse. So this expression over here, so it's minus dkg times the F inverse KS okay, both of them computed on F minus 1. Okay, so this is, so the summation is over K, so this is a number lambda S. And so I'm summing lambda S times these quadratic forms conjugated with AT, and I know that the quadratic forms have an upper bound. If this coefficient is negative, I am in business because here I have a minus 1. And so here I would have a sum of pluses, and then I have all quadratic forms for which I have an upper bound, and they're conjugating with this A transpose and A. Okay, so now it's exactly the algebraic counterpart of having this G prime composed F to the minus 1 times F prime composed F to the minus 1, changing sign. Now I have to show you that that is the case. So what I want to show you is that, and you see, it's a scalar product between the gradient of G and the column vectors of the inverse of the derivative of F. Okay? So I just want to show you the following. So gradient G composed with F to the minus 1. And here I'm really like, looking at okay, so let me really do it this way. So in here I really have df to the minus 1 ks. So this thing composed with f to the minus 1, I have to show you that it is negative. Okay. Let me look at the picture in 2D. Okay, so let me convince you about this in 2D. So what is this guy? So this guy is going to be the inverse of the differential of f, and I'm just looking at the columns, which is the same as to say, let me fix S. So S can be either E1 or E2. Okay. And let me here look at the place where F inverse is going. Okay. So what you're looking at is at F inverse, say, of this segment. This is a curve gamma. So this is the F inverse of the segment E1. Okay. And you're looking at the tangent to this curve gamma. The tangent to this curve gamma is exactly the image through this matrix of this vector. Okay. And then here I have the gradient of G. And what I want to show you is that the gradient of G is pointing in that direction. Okay. So okay. What do I know about this curve? On this curve, the F2 component is actually constant, right? It's constantly equal to the value over here. This is my point, say P. So if the F2 component is constant, the gradient of F2 better be orthogonal to gamma. Okay. Let me draw. Do we have colors? Yeah, maybe yes. So here, okay, it's a green which has become white. Okay, so this one is the gradient of F2. Okay, and now I know that the gradient of F1 has to be obtuse, right? I mean, it has to form an obtuse angle, but F1 is increasing in this direction. So it certainly has to have positive scalar product with this guy, right? So gradient of F1 is somewhere like this. Okay, let me draw this picture better here. So this is gradient of F2, this is gradient of F1. This is our vector over here. So let me call it W. Now gradient G has to have a negative scalar product with gradient of F2. So it must be precisely on this half space, right? But it must have also negative scalar product with gradient of F1. So it must be in this half space. So gradient G is pointing in this direction. So gradient G has a negative scalar product with that, which is what we wanted for having whatever this coefficient, or like somehow this one negative. So all of the coefficients which are actually entering in that expansion, they are negative.
And this also works in higher dimensions, right? I mean,
this also works in higher dimension, hopefully. I need to try to make that, but okay. So in higher dimension, the guy will be orthogonal to all of the others, and there's going to be all of these planes. And yeah, I don't believe there's a problem over there.
Right. It seems like, I mean, you'll have a hyperplane and
Yes.
these two vectors will be on opposite sides. But
Now, what time is it?
25.
25. Okay. So now let me try to explain you what Perelman. So this is my kind of interpretation of what he's doing in the Euclidean space, as far as I can understand. Okay. Now his proof is supposedly like a page and a half, or maybe even less, maybe a page, something like that. But so first of all, so he's essentially claiming the very same theorem on Alexandrov spaces. So on Alexandrov spaces, it would be give me n functions which are semi-concave and whose gradients have these scalar products which are kind of orthogonal to each other. Then give me another function g which is semi-concave and such that the scalar product of the gradient of this function together with the others is okay. And make the f1 fn by Lipschitz. Okay, then compose g with f to the -1 and you actually get a semi-concave function. Okay, so how do I define the scalar product in Alexandrov spaces? This is really genius though. So definition. So first of all, if you have a semi-concave function and you fix a point and you fix a geodesic, on the geodesic you have a concave function up to addition of this t squared. So in particular, your function is differentiable here at this point as a differential of the segment, right? So I'm just using the following. So a convex function or concave function is always differentiable from the right and from the left at every point. So this means I have a directional derivative for every direction. Okay, so define this directional derivative for any direction on the good points. I mean, but you can do this even in general somehow on sigma x. Okay, so define this as the differential of your function f. So dfx now goes from sigma x into r. Okay, so that's the differential. And now comes, okay, so now this, it took me really a lot of efforts to understand exactly what he's defining, because just the notation is ugly, but he's doing this inductively. So if the Alexandrov space is of dimension 1, then you just have 2 points. And take the product of the derivative on the 2 points. So I want to define the scalar product dfx dgx. Okay. So if your Alexandrov space is 1-dimensional, the cone is going to be 2 points, and define the scalar product of the derivative to be like, you know, the product of the derivatives of these 2 points time plus the product of the derivatives at those 2 other points. Okay, so this is going to be like, you know, dfx -1, df dgx at -1 plus dfx at 1 dgx at 1. Actually, the Alexandrov space, even the 1-dimensional one, could be just a single segment, in which case there's only 1. Okay. Okay, now give me a 2-dimensional Alexandrov space. So I can think that this function is a function over the set of directions, which is now a 1-dimensional Alexandrov space. Note that this function is actually concave. That's a little lemma that you have to give.
But it should be concave in a different part.
The same as concave. That's
Concave on the set of directions.
yes, as a function on the Alexandrov spaces.
Well, on
Alexandrov
the circle, it would be like sine, so it has its positive and negative.
I mean, if you were a linear function, you're fine, for instance.
I don't understand. So, like,
So say that you're smooth. Say that you're smooth.
yeah,
Your derivative would be a linear function.
yes, but as a function on this circle, it would be the restriction of a linear function on that circle. So as a function on that circle, it would have concavities both ways.
As concavity in both ways. Okay.
Like it is bounded. on the
Yeah,
convex set.
it is. Okay, so let me just look at what he's saying exactly here. That's a very good. Okay, he calls it spherically concave. What does it mean? Okay, let me put it this way. So if you make the one homogeneous extension, you are concave.
Should it be clear?
I mean, on the Euclidean space, it's because it would be like a rescaling, because what are you doing? You're somehow subtracting the constant so that you put it equal to 0. And then somehow you're just rescaling by the homogeneous rescaling, which makes it Lipschitz. And it's a sequence of semi-concave functions. But the constant, when you do this rescaling, is just going to 0, right? I mean, the constant in the upper bound. So actually, you're just converging towards something which is concave. It doesn't tell anything. I mean, it's kind of, it's stated as a fact. But I believe in the Alexandrov space now you can go and do exactly the same.
Yeah, if it starts with concave function, right?
Semi-concave.
Semi-concave, yeah.
Semi-concave. I mean, the point is that the constant gets redivided. I mean, it gets. I mean, under the rescaling, the second derivative somehow becomes less and less important. So the constant which you put in front of the x squared gets multiplied by a number which is going to 0. So if you buy me that, I think what he calls spherically concave, which he doesn't define, means that the one homogeneous extension to the cone is concave. Okay, now since the one homogeneous extension to the cone is concave, you can actually take the differential again of this function on the circle. And now when you take the differential of the function on the circle, you're back to the inductive assumption. So you know what to do, okay? And so when you are one-dimensional,
I'm not sure what do it is.
you do this. So you take the restriction of the function on the circle, you take the differential, and then you multiply in each point, you multiply the values of the differential at the 2 points, which are like the boundary of the guy.
Yeah, but what do I do with the products of differentials along the circle?
Now, along the circle, for each point, you take the differentials of the differential, you make this scalar product, and then you take the supremum over all points on the circle. So you take the supremum of the fx at the point P, dgx at the point P, so this is for P in the circle, plus the scalar product of the differential as a restriction to the one-dimensional circle. So let me call it, so let's say this is the 0, this is the 1, and this is the fx.
So basically like doing it, picking a flag. So
right. So now on the sphere, I mean, now you induct over the dimension. So on the sphere, what you're going to do is you're going to, like, you're in a three-dimensional space, you take the differential on the space of direction. Okay, in each point, its differential is going to be the guy, and now you take the supremum. Okay, and you continue doing it. Now, just wait a second. So, yeah, exactly. So first of all, it took me a lot of time to realize what the definition was, because this is a line. This is just a line. And then I was just looking at it and saying, what? Okay, so if you have a linear function, it's the usual scalar product. Let me convince you about this.
you're just like
Yes.
Yes.
Yes. Okay, in 1D, if you have a linear function, it's just 2 times the scalar product, right? Okay, now, so here you have a linear function. So if you evaluate the linear function at that point, so let us call it E. So the linear function is, say that the linear function f of x is v scalar product with x, right? So that is the gradient of the linear function. Okay, so v scalar product, v scalar product with E at this point is the evaluation of the is what we call dfx at E, right? Or at P. Now, this is not in S1, but this would be in whatever, the sigma 1. So sigma 1 now here is S1. Okay,
Maybe just
now,
maybe be short, like you're picking tangent direction.
yes,
Pick
yes.
a point on the tangent
Yes.
cone, pick a tangent direction, etc. So you
Yes,
kind of normal frame and-
but look at it. So now here, what is the, so this is the perpendicular direction, right? Okay. And when you differentiate,
you're just computing regular style.
this is a linear function. So when you differentiate, you get again the linear function. And you're taking the linear function scalar product with E per. So when you're taking V and when you're evaluating A and when you're evaluating on this point, which is in the tangent, you're actually getting this guy, right? Okay, so now this one here is VEWE, and then it's going to be the evaluation of the 2 differentials on, which is VE per WE per, right? But E and E per P is a basis. So this one is just the scalar product between V and W. And it's irrelevant, it's a constant function. So somehow the observation is that this procedure, if you apply it for a linear function on on the Euclidean space, is just built in such a way that when you're going to do this last supremum, nothing is happening actually. You just have a constant, and the constant is just the scalar product of all these guys. Okay, so with this definition, you can, at this point, state the same lemma that we had before. So you can just say, okay, let F1, Fn from an Alexandrov space into some open set V in N, P by Lipschitz. Assume, I mean, this you can define as, if you want this, you can understand as the scalar product of differential. So like, okay, so now assume the Fi, the Fj is less or equal than say minus epsilon for all I different than j, and assume, okay, and semi-concave. Assume the Fj dg is also less or equal than minus epsilon for every j, and g is semi-concave. Okay, then g composed with f to the minus 1 is semi-concave.
Sorry, I'm a bit concerned. I mean, you're taking more derivatives, right? I mean, why is the second derivative of f defined here in this inductive definition?
Because each time it's a semi-concave function, right? Actually, after the first time, it's a concave function.
Because only when you restrict it on the,
It's a one homogeneous concave function. So you can differentiate it. I mean, now don't be fooled, right? I mean, if I'm looking at the derivative as a function, so if I do it the first time, okay, it's a linear function, and then I'm differentiating the linear function. So I just keep the linear function. I'm not really taking higher derivatives in a situation in which I'm smooth.
right, but in an Alexander space, okay, I have.
Well, in an Alexander space, what happens is that instead of having like, you know, this differential, instead of being somehow linear function, it's still a concave function.
Okay.
Which is one homogeneous.
Okay.
Now, when I'm differentiating in the orthogonal directions, I'm picking up another concave function, which is going to be like, you know, homogeneous in this direction, and then it's going to be homogeneous in this other direction. So then it's becoming like, you know, homogeneous in two directions. And so you're not doing anything but kind of flattening directions one after the other.
I see. Okay, that makes sense.
It's like making blow-ups of blow-ups for, say, area minimizing cabinets. It's the same
If
thing.
you actually have zero, is it obvious then? I mean, if they're all orthogonal, would it be obvious or?
I know, okay. So the fact that there's a little bit of space, I mean, this leeway, this minus epsilon, I think it's important in the Alexandrov context. Of course, for our computation, that was okay.
Well, I just meant if it were actually zero. Well, I see. So it means it's not zero. Okay, well,
Yeah, it's not zero, it's really like negative. Now, in the Euclidean space, I think this wouldn't matter, right? I mean, the proof that I gave you, I just need a sign, so less or equal than zero would be equally fine.
I see, so,
right?
So it doesn't simplify it.
I doubt strongly. I was like, you know, trying to
just to get some intuition.
Yeah, to get some intuition. I don't quite have an intuition myself.
Right, I mean, somehow,
Okay, and his proof, I'm stuck at his proof at the first line. But you will see that there is something like that picture. So his proof goes in this way. So he says, let me take a segment in the arrival space. And now on that segment, I want to show that the restriction of the function has the semi-convexity property. Okay. Okay, so let me look at the image of this through f to the -1. Okay, it's a curve gamma. Okay, the first statement is that it's not difficult to see that this curve gamma, and let's say this is 0, right? So this is the point in which you're interested, but you want to prove like. And so here there's, say, gamma of 0. So let's say, let's call this point P. No, it's really 0. So this next one is here. So he says, first of all, it's not difficult to see that it's right and left differentiable. Okay. Because it's by Lipschitz. Well, because it's by Lipschitz, certainly not. But maybe because the original guy is semi-concave, I can try to cook up the differentiability at that point. I can believe this. So I can believe that if you give me a semi-concave function, which is differentiable from the right and from the left in a classical sense everywhere, if I'm looking at its inverse, it's going to be differentiable as a function of one variable. So that I might believe. But then he says, okay, gamma dot 0 now dg, so this here, so dg of gamma dot plus 0 plus dg of gamma dot minus 0 is less or equal than 0. Okay, so now if the function is really differentiable, this condition is the condition that I showed you previously. But okay, if it is the orthogonal, I mean, if it is the horizontal direction and the vertical direction, I can prove it. But if it is a general direction, I actually don't see why it even should be correct. I mean, like stated in this way, I even have counterexamples. So somehow, if you remember my picture before, I was using, right? I was using this tangent over here. Then I was using the fact that, okay, so here is gradient of F2. Here is gradient of F1. Right? And I was using that this guy is over here. But if the segment is in some direction which is not, you know, E1 or E2, and it starts getting like, I don't know, if it's going like this way, then I don't see how this picture can possibly be correct. And I don't know how to conclude the proof that he's actually like, you know, proposing. Of course, in the Euclidean space, I mean, then I started thinking, okay, maybe if I have it on the like, you know, on the main axis, I mean, on the coordinate axis, maybe that is enough. And that's how I came up with the proof that I showed you. So on the Euclidean space, of course, having that property on the main axis is exactly what you need to make that sum positive and to get the semi-concavity. But in the general case, I don't know. Okay, so he's arguing that if this were false, then there would be a vector v for which okay, there would be a vector v for which the evaluation of this guy is going to be positive, and in the definition of the differential, that would be a problem. But okay.
In the Euclidean setting, if everything was smooth, that would be exactly equal to 0, right?
Sorry?
In the Euclidean setting, if everything was smooth, that would be exactly equal to 0. No?
What do you mean that would be exactly equal
the
to
less
0?
than equal to would be identically 0.
No, because this one he takes, I mean, he takes it in the same direction. I mean, it's just, it's not this one, that one.
Ah, it's not that. Okay.
No. It's really this one. I mean, it's that it could make a king, but
yeah, it could make a king, but if it didn't, then
yeah, but it's the segment is oriented in a certain direction. You're taking the derivative anyway, going that way, right?
Maybe sorry, I'm not understanding that. What is the gamma dot plus and gamma dot minus?
Okay, it's not differentiable at the point.
Right.
It has a right and left limit.
Sure. But say it were differentiable at the point, but then they will be in opposite directions, no?
No.
Ah, okay, I understand. Sorry. Yes. Yeah. Okay, fine. Right.
That's what he's doing.
Okay.
Or I mean, if you want, you can of course to take the kind of, you know.
Yeah.
This definition, but then you have minus epsilon over here.
Yeah. Okay, yes.
No, at the point of differentiability, that is just
so there it's
the differential of the function.
fine. Okay, then it's yes. You have, okay.
I mean, the fact that you're not differentiable, okay, it's a technicality, but why in the hell, if I take any straight segment, I would have that condition? Search me. I think I have an example. Huh? I mean, I'm not. I think you just take enough. I mean, you take a linear function, whatever linear function that you might like. I don't know, some linear function like this, right? Okay, so that is f of x equal to I don't know. Okay. Then I take another linear function, which is g of x is equal x2 0, x2, right? So the gradient of g is 0 minus 1. Okay, now f to the minus 1 I can compute explicitly. Okay. I actually made an error in my computation then. I had the minus in a wrong place. Well, anyway, so it's interesting to check on some simple example like this one. So, this is one guy. Let's see. So. Right. Yeah, this pattern on hard. So how's the inverse of the function? I have to, in the inverse of a matrix, I have to exchange those guys, and then I have to change the sign. So I guess.
I'm not sure what is
It's okay.
function.
It's okay. It's okay. This one, and this one should be something like this, right? This is F inverse. I'm just inverting this matrix. Oh, and okay, and then there is the determinant, right? And the determinant is this guy. I mean, I'm dividing by the term. So then I would have right? Sounds correct. So let's see. This one's scalar product with this one gives me 1. This one's scalar product with this one gives me 0. This one's scalar product with that one gives me 0. And this one's scalar product with that one gives me 1. Okay, so this is F inverse X. Okay, so now take a segment in some direction and take the segment in that direction and what do I want to do? So I want to compute the differential of f the differential of g along any of these guys, right? I really don't see how you can have a positivity condition, right? So that, I mean, that differential is on 2. So
Is that satisfied? The dfj dg is less than 0. For the,
sorry?
the condition dfj inner product with dg is negative. That doesn't look like it's satisfied, right? Because one has 1/3, 1 over root 3, 1, and the other is 1 over root 3, negative 1.
Ooh. Okay, so this would be
No, it would be on f, not on inverse.
this would be no, it's on inverse. It's on inverse. But even on the inverse, it should be satisfied, right? So ooh. But it doesn't even work with my proof, you mean?
Yeah, I don't see why that condition is satisfied. dfj dg is less than 0.
Sorry. Okay, it's this one.
Yeah.
Okay. Okay, with that one, it changes a lot, right? Now this changes. And I think this changes, right?
Well, the determinant is the
Okay, so now the determinant is different. Sorry, you're right.
no, the determinant is the same. Sorry.
No. The determinant is positive.
Mhm.
Okay, so now this one is 1/2. This one is square root of 3 divided by 2. This one is plus square root of 3 divided by 2. This is minus 1/2. Okay, so now we have 1 over square root of 3 minus, and then we have +1 plus 1. Okay, you agree? One,
Yeah.
0, 0, 1. Okay, so now you see that. Okay, so now you see I am consistent with my. I mean, okay. So what is the scalar products that we checked previously? Is the scalar product with the column vectors, right? And I mean the column vectors has a 1 and a 1 over here, and my gradient G has 0 minus 1. So if I look at the horizontal direction and the vertical direction, and I look at the image, that condition on the sign is correct.
Yeah.
But I'm not understanding how it is going to be correct on a general segment.
Right. Yeah. Okay.
Yes, like
Yeah.
really fail to see that.
I don't understand, like, the condition, the dg and the dfi being negative, like if what is f1 here?
Okay, F1 is this function.
Oh, okay. Yeah, sorry.
And F2 is this
Yeah.
function. And so the gradient of F1, so that's why the picture I was picturing are the gradients, right? So this is gradient F1, gradient F2, this is gradient G. So on the horizontal and vertical segments, I'm perfectly fine with this condition, but I'm not understanding what is going on in the other segments. I have no explanation for that. And then, okay, I mean, this is the starting point of the proof. Maybe it's not important. I mean, maybe the sign doesn't. Maybe the sign is not an important point. I don't know. Well, anyway, so I've not even started with what should have been kind of the rest, which is that on the so on top of this metric, I mean, on top of this structure, you can put a Riemannian metric, which is a C0 Riemannian metric, and it has BV coefficients. I mean, it's C0 outside of the, so this DC, okay, so there's this DC charts now, and now you will get something which is going to be continuous outside of the points where the charts are not continuous. I mean, continuous where the charts, so the charts have some special points which are bad.
Right.
Those are also the special points where the metric might not be continuous. But on the complement, it's a Riemannian metric, it's a continuous Riemannian metric, it's bounded away from zero. And also the derivative is a measure, so it's a function of bounded variation. And for instance, you can make sense of the Christoffel symbols out of this.
This is after showing that it's a DC manifold, right?
This is this is an independent paper. So
okay.
So there's this paper by Otsu and Shioya.
Right.
They show that there is this continuous Riemannian metric, and they show that it is the same. I mean, they show that the distance is induced by the Riemannian metric.
Okay.
So it's really the geodesic distance compatible with the Riemannian metric. Okay, then in the preprint he's saying, okay, so the charts are actually DC, and the metric is function of bounded variation. But so the existence of the metric, I think, is like, it's a published paper on JDG in 1994 by these two Japanese guys. I mean, it's 30 pages, but you can go through the whole details and check, and it seems kosher. Once you have these DC charts, the fact that the metric is BV is some integration by parts, something.
But why is actually DC important? Isn't it? Like, what's the difference between DC and just having like the semi-continuous functions? Like, is there any place where
semi-concave?
Semi-concave, yeah. Sorry. Like, why couldn't everything be defined as semi-concave?
Keeping positive curvature condition.
Okay. He can't even prove it. I mean, I couldn't prove it. Okay, so you need to. I mean, once you have this lemma, right, to get the condition that the derivative, that the scalar product of the gradient of the function is less than 0, you need to add a function.
Okay, yeah.
And that function that you're adding is concave.
Right, okay.
And it's directed in such a way that it makes the scalar product with all of these other guys negative. So you're not applying it to the function which gives you, say, the other coordinates, but you're applying it to an adjustment of that function. And so effectively, you're not writing the composition. The change of coordinates is not a semi-concave function, but it's a difference of semi-concave functions. Okay. So I don't think you can do without that. But okay, so I can give you an idea of in the next lecture. I can give you an idea of how you can use these DC charts and what the Japanese guys. So the paper by Ambrosio, which I thought does the stuff, it doesn't. I mean, they explain you what is the DC calculus and all the things, but then when it comes to this theorem, they tell you, okay, part A is proved in Perelman and part B is proved in whatever, Otsu and Shoya. The geometric idea of this paper is clear. Then there's plenty of details. It's a 30 pages paper. I think the integration by parts, after you assume that this guy is a DC coordinate charts, is kind of okay. But what I'm slightly concerned about is, the rest of the seminar, because, okay, there's not really material that it seems like understandable, if I have to tell you this. I mean, the first
machinery required for all the possible further directions.
Sorry?
Is the machinery of these DC manifolds required for all the possible directions?
No, I don't think so. So I think, for instance, if you want to prove the stability, you can avoid it, and you can use this other thing that he actually does in the published paper, which he calls there. So, and that is what Kapovich is doing. So now this there just says something like, okay, the charts or the function for which I want to compute a differential, they are functions by linear combinations of concave functions computed on distance functions. And so for the distance function, I can just tell you right away what I'm guessing to be the derivative. It's just the geodesic directed from the point B to the point whatever at which you're arriving, and that direction. And if I give you a function which is the sum of this expression, I'm just going to use the chain rule with the composition and just going to use linearity. And that I define to be my derivative. There's a little scary observation which says the derivative might not be unique because I might have two different representations of the functions with different ways. But you don't have to be worried about that. It's a little bit, I'm a little bit nervous. If I define the differential of something, I'd rather have to be like, the function. I would like something like locality. If the function is the same somewhere, the function is the same everywhere, and you can't tell me if the derivative is the same. I'm a little bit concerned by your concept of derivative.